Planet Earth. If you look closer, you'll see that a whole other world exists beneath the surface of land and sea. Layer after layer of rock structures go deep into the Earth's crust, mile after mile. And trapped within these structures, along with other liquids and solids, you'll often find deposits of oil and natural gas, the world's two most important sources of energy. These famous fuels are in constant demand because they make the world go round, day in and day out. So how do you find something that's completely hidden beneath the Earth's surface? It's a mystery that people in the oil and gas industry are always trying to solve, and for very good reason. Drilling for hydrocarbons is expensive. And before they spend money on equipment and crews, exploration and production companies need a reliable strategy for pinpointing where to drill. Geoscientists have a secret weapon called seismic exploration, and it involves sending acoustic energy, which takes the form of wavelets, into the ground to get a sound picture beneath the surface. It's complicated, so let's start with the analogy of bats. Bats can't see very well, so they send out little waves of sound that bounce off of objects and then go back to their ears. It's called sonar. It gives them what you might call a sound picture of their world. That's a good example of how nature already uses a form of seismic acoustic imaging to locate objects. Doctors also use it for ultrasound imaging. Geoscientists use man-made tools to make the sound wavelets, listen to them, and then record them. When you want to know if oil and gas deposits are in a particular area, geophysical companies bring large trucks that have big vibrators on them. Most of the time, this is what generates the acoustic energy or vibration. They use geophones, or very sensitive seismic microphones, to hear the reflected sounds, but sometimes they set off small buried charges. They set many geophones on the ground in a line, and they are attached to a recorder inside another truck. The vibrators send thousands of wavelets down into all the different layers of the Earth. Some of the wavelets bounce off of the boundaries between the rocks below the surface and are reflected back to the geophones that are waiting to record them. Each geophone along the cable sends the received wavelets to the recording truck where they're recorded and stored. How do the wavelets reach into the subsurface of the ocean? That's offshore seismic, and it just requires a different device to send out the wavelets and record those that are reflected back. Out at sea, a seismic crew works off a vessel with a specially designed back end, so it's easier to lay floating cables or streamers. And all along the length of the streamers, microphones, called hydrophones, are attached one after another. Several of these hydrophone streamers are pulled behind the vessel at once. Acoustic sources are towed behind the vessel in front of the streamers and release compressed air, which creates the wavelets. These wavelets travel through the water and into the subsurface below, where, just like on land, they bounce off the rock layers and then return to the hydrophones to be recorded. Here's what seismic looks like after it's been recorded. Basically, it's a bunch of squiggles. There are still a few more steps to go before it begins to look like an actual picture of the Earth's interior. Right now, the data is still in its raw form. To get a picture that actually looks like the Earth beneath us, the data has to be processed. It takes a large supercomputing PC cluster to process the seismic data. These computers go through all the different traces made by the wavelets and filter out everything we don't need, such as vibrations made by a tractor in a field nearby. Using really amazing computer applications and working on state-of-the-art workstations, geoscientists can see the seismic data translated into a 3D picture. You might be thinking, I don't see any oil and gas there. But believe it or not, geoscientists can look at this processed data with their trained eyes and make an informed decision about whether or not oil and gas deposits are in the geologic structures. Seismic data leads to a high percentage of drilling success with less risk to the environment. And in a world where the demand for oil and gas is increasing faster than the supply, good seismic information will lead to more affordable energy.
Millions of dollars can be spent drilling an oil or gas well, so it is very important to gather as much information as possible at every stage to determine if it makes good business sense to continue drilling and complete the well. Logging a well is one very effective way oil and gas companies gather detailed information about the different layers of rock they've drilled through. This gives greater certainty about whether or not hydrocarbons are present. If the well is not promising, the process can be stopped and the well abandoned before incurring the large costs of completing the well. Once the well has been drilled to its target depth, the drill pipe and bit are removed from the hole. A specialized logging crew and equipment are brought on location. The crew assembles a probe, which is several different logging tools connected together. Depending on the number of tools in the assembly, the probe may be 70 to 120 feet in length. Using diverse scientific techniques, each tool performs a different kind of measurement of the rock and fluid properties within the geological formations surrounding the wellbore. The probe is lowered down into the wellbore on a wire line until the top of the probe is below the target depth. The process is carefully monitored by the well logging crew and geologists. As the probe is raised back up the hole, the various logging tools are activated by computers on the surface that produce a graph called a well log, which represents the geologic properties of the layers below the surface. On the well log, the gamma ray tool measures any radiation emitted by the rocks. Rock with lower amounts of radiation is called cleaner rock, such as limestone and sandstone. These are more likely to contain hydrocarbons than dirty rock. Notice that near the top of the log, the line is relatively flat and the reading is consistently high, indicating dirty rock, likely shale. But near the bottom, the reading fluctuates because the logging tool is entering a sandy area which has little radiation and could contain oil or gas. This data is called the apparent water resistivity curve. It indicates the potential for water in the rock formations surrounding the wellbore. At the top of the log, the line is at the left, which indicates more than likely the formation is wet or shaly. As we move down the log, the measurements change drastically. This indicates a quickly changing mixture of shale or other water-bearing formations on the left, to sand with the possible presence of hydrocarbons as the curve moves to the right. This next reading, called the spontaneous potential curve, shows geologists when the instrument passes from one rock formation to the next. The spontaneous potential tool uses two sensors, one at the surface and one down the hole, to compare the natural electrical charges at the surface with the underground rock. Some layers of rock have a positive charge compared to the surface, while others have a negative charge. A shift to the right on the log indicates a positive charge, usually associated with shale. A shift to the left indicates a negative difference, usually associated with sandstone. The center section of the log shows readings from the resistivity tool. The overlapping lines are 6 resistivity curves, each one measuring at a different distance from the wellbore how well the rock conducts electricity. The left side of the grid shows less resistance to electricity, while the right side denotes greater resistance. Oil or gas-bearing rocks are less conductive and therefore more resistive to electrical currents. Notice that for most of the vertical distance, the rock has less resistivity. This is likely shale. The higher resistance is likely an indicator of sand, a layer that can hold hydrocarbons. The reading from the neutron porosity tool, which can count how many hydrogen atoms are in the surrounding rock, can be seen in this section of the log. A higher concentration of hydrogen indicates the possible presence of oil. When the curve moves to the right, this indicates fewer hydrogen atoms, so as we move down the wellbore, we can see that the amount of hydrogen is generally decreasing. This means there is either very tight rock that cannot hold oil, or gas may be present. Working in tandem with the neutron porosity tool is the density porosity tool. It measures the space between the electrons in the rock, also known as bulk density. Near the top of the log, there is a greater amount of density, but as we move down the wellbore, the log indicates that the rock is becoming less dense. You'll notice that in this section, the density porosity curve and the neutron porosity curve cross over. This is significant. Whereas the neutron curve indicates either tight rock or gas, the density porosity curve tells us that the rock is more porous and therefore cannot be tight rock. This area indicates the high probability of natural gas. The next curve represents the measurements taken by the sonic tool. It shoots sound waves into the formation and records the time they take to return. Dense rock will have a faster travel time, while porous rock will be slower. Finally, on the left edge of this section, we see the reading from the caliper tool, which measures variations in the size of the wellbore. These variations can affect the accuracy of the other tools on the probe. So based on this measurement, the computer recalibrates the readings from the other tools as necessary. These are the most common logging tools used by oil and gas companies to gather information about the rocks and any fluid or gas content thousands of feet below the surface. There are numerous other tools designed for specific logging situations. The more complicated the geology is, the more diverse the set of logging tools needs to be. None of these tools by themselves can provide sufficient information to make an informed assessment about the well. But combined, these tools offer a more comprehensive and reliable perspective. When trained geologists look at well logs such as this, there is enough information for them to literally envision what the subsurface looks like. Because most wells are logged, oil and gas companies can research these logs to evaluate prospective drilling sites. When a company plans to drill in a new area, they can look at the logs of nearby wells called control wells. Lining up the logs, adjusting for variations in the surface altitude of each well, the geologist can get a good idea of the rock structure and possible presence of hydrocarbons across the area. This information is very helpful in identifying promising well sites before drilling begins. With this information, oil and gas companies can drill new wells with greater confidence and promise of success.